The Wilkinson Microwave Anisotropy Probe, originally known as the Microwave Anisotropy Probe, was a spacecraft operating from 2001 to 2010 which measured differences across the sky in the temperature of the cosmic microwave background, the radiant heat remaining from the Big Bang. Headed by Professor Charles L. Bennett of Johns Hopkins University. The mission was developed in a joint partnership between the NASA Goddard Space Flight Center and Princeton University. The WMAP spacecraft was launched on June 30, 2001 from Florida. The WMAP mission succeeded the COBE space mission and was the second medium-class spacecraft in the NASA Explorers program. In 2003, MAP was renamed WMAP in honor of cosmologist David Todd Wilkinson, who had been a member of the mission's science team. After 9 years of operations, WMAP was switched off in 2010, following the launch of the more advanced Planck spacecraft by ESA in 2009. WMAP's measurements played a key role in establishing the current standard model of cosmology, the lambda CDM model. The WMAP data are very well fit by a universe that is dominated by dark energy in the form of a cosmological constant. Other cosmological data are also consistent, and together tightly constrain the model. In the lambda CDM model of the universe, the age of the universe is 70013772000000013.772 plus or minus 0.059 billion years. The WMAP mission's determination of the age of the universe to better than 1% precision was recognized by the Guinness Book of World Records. The current expansion rate of the universe is of 7001693199999999999999999999999999999999999999999999999999999999999 plus or minus 0.80 kilometers s-1 mpc-1. The content of the universe presently consists of 69984628000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 matter 69992402000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000016 cold dark matter that neither emits nor absorbs light, and 69997134999999999999971.35% plus 0.95% minus 0.96% of dark energy in the form of a cosmological constant that accelerates the expansion of the universe. Less than 1% of the current contents of the universe is in neutrinos, but WMAP's measurements have found, for the first time in 2008, that the data prefers the existence of a cosmic neutrino background with an effective number of neutrino species of 70032600000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000ɔ Euclidean flat geometry, with curvature radiation. The anisotropies then are used to measure the universe's geometry, content, and evolution, and to test the Big Bang model, and the cosmic inflation theory. For that, the mission is creating a full sky map of the CMB, with a 13 arc-minute resolution via multi-frequency observation. The map requires the fewest systematic errors, no correlated pixel noise, and accurate calibration, to ensure angular scale accuracy greater than its resolution. The map contains 3,145,728 pixels, and uses the Heel-Pix scheme to pixelize the sphere. The telescope also measures the CMB's E-mode polarization, and foreground polarization. Its life is 27 months, 3 to reach the L2 position. 2 years of observation. Development. The WMAP mission was proposed to NASA in 1995, selected for definition study in 1996, and approved for development in 1997. The WMAP was preceded by two missions to observe the CMB, the Soviet RELIKT-1 that reported the upper limit measurements of CMB and isotropies, and the U.S. COBE satellite that first reported large-scale CMB fluctuations. The WMAP is 45 times more sensitive, with 33 times the angular resolution of its COBE satellite predecessor. The successor European Planck mission had a higher resolution and higher sensitivity than WMAP and observed in 9 frequency bands rather than WMAP's 5, allowing improved astrophysical foreground models. Spacecraft. The telescope's primary reflecting mirrors are a pair of Gregorian 1.4 meters by 1.6 meters dishes that focus the signal onto a pair of 0.9 meters by 1.0 meters secondary reflecting mirrors. They are shaped for optimal performance. A carbon fiber shell upon a Corex core, thinly coated with aluminium and silicon oxide. The secondary reflectors transmit the signals to the corrugated feed horns that sit on a focal plane array box beneath the primary reflectors. The receivers are polarization-sensitive differential radiometers measuring the difference between two telescope beams. The signal is amplified with HEMT low-noise amplifiers, built by the National Radio Astronomy Observatory. There are 20 feeds, 10 in each direction, from which a radiometer collects a signal. The measure is the difference in the sky signal from opposite directions. The directional separation azimuth is 180 degrees. The total angle is 141 degrees. To avoid collecting Milky Way galaxy foreground signals, the WMAP uses 5 discrete radio frequency bands, from 23 GHz to 94 GHz. The WMAP's base is a 5.0 meters diameter solar panel array that keeps the instruments in shadow during CMB observations. Upon the array sit a bottom deck and a top deck. The telescope's cold components, the focal plane array and the mirrors, are separated from the warm components with a cylindrical, 33 cm long thermal isolation shell atop the deck. Passive thermal radiators cool the WMAP to California, 90 degrees K. They're connected to the low-noise amplifiers. The telescope consumes 419 W of power. The available telescope heaters are emergency survival heaters, and there is a transmitter heater used to warm them when off. The WMAP spacecraft's temperature is monitored with platinum resistance thermometers. The WMAP's calibration is effected with the CMB dipole and measurements at Jupiter. The beam patterns are measured against Jupiter. The telescope's data are relayed daily via a 2 GHz transponder providing a 667 kbit per second downlink to a 70 meters deep space network telescope. The spacecraft has 2 transponders, one a redundant backup. They are minimally active. California, 40 minutes daily, to minimize radio frequency interference. The telescope's position is maintained in its 3 axes, with 3 reaction wheels, gyroscopes, 2 start trackers and sun sensors, and is steered with 8 hydrazine thrusters. Launch, trajectory, and orbit. The WMAP spacecraft arrived at the Kennedy Space Center on April 20, 2001. After being tested for 2 months, it was launched via Delta II 7425 rocket on June 30, 2001. It began operating on its internal power 5 minutes before its launching, and so continued operating until the solar panel array deployed. The WMAP was activated and monitored while it cooled. On July 2, it began working, first with in-flight testing, then began constant, formal work. Afterwards, it effected 3 Earth-Moon phase loops, measuring its side lobes, then flew by the Moon on July 30. en route to the Sun-Earth L2 Lagrangian point, arriving there on October 1, 2001, becoming, thereby, the first CMB observation mission permanently posted there. The spacecraft's location at Lagrange 2 minimizes the amount of contaminating solar, terrestrial, and lunar emissions registered, and thermally stabilizes it. To view the entire sky, without looking to the Sun, the WMAP traces a path around L2 in Ilias orbit, California, 1.0 degree to 10 degrees, with a 6-month period. The telescope rotates once every 2 minutes, 9 seconds, and precesses at the rate of 1 revolution per hour. WMAP measures the entire sky every 6 months, and completed its first full sky observation in April 2002. Foreground radiation subtraction. The WMAP observes in 5 frequencies, permitting the measurement and subtraction of foreground contamination of the CMB. The main emission mechanisms are synchrotron radiation and free emission, and astrophysical dust emissions. The spectral properties of these emissions contribute different amounts to the 5 frequencies, thus permitting their identification and subtraction. Foreground contamination is removed in several ways. First, subtract extant emission maps from the WMAP's measurements. Second, use the components' known spectral values to identify them. Third, simultaneously fit the position and spectra data of the foreground emission, using extra data sets. Foreground contamination also is reduced by using only the full sky map portions with the least foreground contamination, whilst masking the remaining map portions. Measurements and discoveries. 1-year data release on February 11, 2003, NASA published the first year's worth of WMAP data. The latest calculated age and composition of the early universe were presented. In addition, an image of the early universe, that contains such stunning detail that it may be one of the most important scientific results of recent years, was presented. The newly released data surpass previous CMB measurements. Based upon the Lambda CDM model, the WMAP team produced cosmological parameters from the WMAP's first-year results. 3 sets are given below. The first and second sets are WMAP data. The difference is the addition of spectral indices, predictions of some inflationary models. The third dataset combines the WMAP constraints with those from other CMB experiments, and constraints from the 2 decifarads galaxy redshift survey and Lyman alpha forest measurements. Note that there are degenerations among the parameters. The most significant is between IM. The errors given are at 68% confidence. Using the best fit data and theoretical models, the WMAP team determined the times of important universal events, including the redshift of reionization 7003117 plus or minus 4, the redshift of decoupling 700310890000000001089 plus or minus 1, and the redshift of matter, radiation equality 7003323300000003233 plus 194 minus 210. They determined the thickness of the surface of last scattering to be 7012500000000000195 plus or minus 2 in redshift, or 701237237968000000118 plus 3 minus 2 kyr. They determined the current density of baryons 699325000000000000000 times 10⁻⁷ cm-1, and the ratio of baryons to photons 699061000000000000000000000000000000000000000000000000000000000000000000000000000000000 plus 0.3 minus 0.2 times 10 minus 10. The WMAP's detection of an early reionization excluded warm dark matter. The team also examined Milky Way emissions at the WMAP frequencies, producing a 208-point source catalog. Also, they observed the Sunyaev-Zeldovich effect at 2.5 sigma. The strongest source is the Coma cluster. 3-year data released. The 3-year WMAP data were released on March 17, 2006. The data included temperature and polarization measurements of the CMB, which provided further confirmation of the standard flat lambda CDM model and new evidence in support of inflation. The 3-year WMAP data alone shows that the universe must have dark matter. Results were computed both only using WMAP data, and also with a mix of parameter constraints from other instruments, including other CMB experiments, SDSS, the 2 decifarads Galaxy Redshift Survey, the Supernova Legacy Survey, and constraints on the Hubble constant from the Hubble Space Telescope. Optical depth to reionization improved due to polarization measurements. B less than 0.30 when combined with SDSS data. No indication of non-Gaussianity. 5-year data release. The 5-year WMAP data were released on February 28, 2008. The data included new evidence for the cosmic neutrino background, evidence that it took over 500 million years for the first stars to reionize the universe, and new constraints on cosmic inflation. The improvement in the results came from both having an extra 2 years of measurements, as well as using improved data processing techniques and a better characterization of the instrument, most notably of the beam shapes. They also make use of the 33 GHz observations for estimating cosmological parameters. Previously only the 41 GHz and 61 GHz channels had been used. Finally, improved masks were used to remove foregrounds. Improvements to the spectra were in the third acoustic peak, and the polarization spectra. The measurements put constraints on the content of the universe at the time that the CMB was emitted. At the time 10% of the universe was made up of neutrinos, 12% of atoms, 15% of photons and 63% dark matter. The contribution of dark energy at the time was negligible. It also constrained the content of the present-day universe, 4.6% atoms, 23% dark matter and 72% dark energy. The WMAP 5-year data was combined with measurements from Type Iowa supernova and baryon acoustic oscillations. The elliptical shape of the WMAP skymap is the result of a Molevide projection. The data puts a limits on the value of the tensor to scalar ratio, r less than 0.22, which determines the level at which gravitational waves affect the polarization of the CMB, and also puts limits on the amount of primordial non-Gaussianity. Improved constraints were put on the redshift of reionization, which is 700110900000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 plus or minus 1.4, the redshift of decoupling, 70031090880000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 radiation equality, 70335300000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 was expanded to include 390 sources, and variability was detected in the emission from Mars and Saturn. 7-year data release. The 7-year WMAP data were released on January 26, 2010. As part of this release, claims for inconsistencies with the standard model were investigated. Most were shown not to be statistically significant, and likely due to a posteriori selection. For the deviations that do remain, there are no alternative cosmological ideas. It seems most likely these are due to other effects, with the report mentioning uncertainties in the precise beam shape and other possible small remaining instrumental and analysis issues. The other confirmation of major significances of the total amount of matter, energy in the universe in the form of dark energy 72.8% as non-particle background, and dark matter 22.7% of non-baryonic particle energy. This leaves matter, or baryonic particles, at only 4.56%. 9-year data release on December 20, 2012. The 9-year WMAP data and related images were released. 70013772000000013.772 plus or minus 0.059 billion-year-old temperature fluctuations and a temperature range of plus or minus 200 microkelvin are shown in the image. In addition, the study found that 95% of the early universe is composed of dark matter and energy. The curvature of space is less than 0.4% of flat, and the universe emerged from the cosmic dark ages, about 400 million years after the Big Bang. Main result. The main result of the mission is contained in the various oval maps of the CMB spectrum over the years. These oval images present the temperature distribution gained by the WMAP team from the observations by the telescope of the mission. Measured is the temperature obtained from a Planck's law interpretation of the microwave background. The oval map covers the whole sky. The results describe the state of the universe only some 100,000 years after the Big Bang, which happened roughly 13.8 billion years before our time. The microwave background is very homogeneous in temperature. Follow-on missions and future measurements. The original timeline for WMAP gave it 2 years of observations. These were completed by September 2003. Mission extensions were granted in 2002, 2004, 2006, and 2008, giving the spacecraft a total of 9 observing years, which ended August 2010, and in October 2010 the spacecraft was moved to a heliocentric graveyard orbit outside L2, in which it orbits the Sun 14 times every 15 years. The Planck spacecraft, launched on May 14, 2009, also measures the CMB and aims to refine the measurements made by WMAP, both in total intensity and polarization. Various ground and balloon-based instruments have also made CMB contributions, and others are being constructed to do so. Many are aimed at searching for the B-mode polarization expected from the simplest models of inflation, including EBEX, SPIDER, BICEP2, Keck, Quiet, Class, SPTPOL and others. On the 21st of March 2013, the European-led research team behind the Planck Cosmology Probe released the mission's all-sky map of the cosmic microwave background. The map suggests the universe is slightly older than thought. According to the map, subtle fluctuations in temperature were imprinted on the deep sky when the cosmos was about 370,000 years old. The imprint reflects ripples that arose as early in the existence of the universe as the first known millionth of a second. Apparently, these ripples gave rise to the present vast cosmic web of galaxy clusters and dark matter. Based on the 2013 data, the universe contains 4.9% ordinary matter, 26.8% dark matter and 68.3% dark energy. On 5 February 2015, new data was released by the Planck mission, according to which the age of the universe is 13.799 plus or minus 0.021 billion years old, and the Hubble constant was measured to be 67.74 plus or minus 0.46 mpc.